Hello friends, welcome to another tutorial in microprocessor and microcontroller series. In today's tutorial we'll talk about interrupts of 8051. It's very important to study the interrupt structure of a microprocessor or a controller to better understand the functioning of the microprocessor or a controller. There are 5 interrupts in 8051 and I've written those 5 interrupts in the order of their priority. The top one has the highest priority and the bottom one has the lowest priority. Now that being said, I'll discuss all these interrupts, where they feature, and while discussing the interrupts, I'm sure you'll recall the functioning of these interrupts also. So the first one is IE0, which is the external interrupt 0. You'll find this interrupt at pin 12 of the dual inline package of 8051. And the third interrupt is the external interrupt 1, and you'll find it on the pin number 13. And both these interrupts are active low. That means if any device is connected at these two pins and if it wants the microcontroller to stop its current functioning and service it, then it has to send an active low signal there. So you could check out the pin diagram again to verify that these two pins, where you'll find the INT 0 and INT 1, which is the external interrupts, you'll find a bar on top of it. So that goes to show that these are active low interrupts. Now the second interrupt is timer overflow 0 interrupt. So this is one interrupt that you'll find if you study the functioning of the timers of the 8051. The timers of 8051 are up timers, or in other words, if we put a value in a timer, it starts to increment until it reaches all ones. So technically it reaches a point of FFFF. So after FF, when the timer is reset back to 00, then this interrupt is generated, and you'll find this interrupt in the TCON register of the timers also. So I'll put a reference of TCON register here. So you need to refer the TCON register once again. The 7th and the 5th bit of TCON register are timer overflow 1 and timer overflow 0 flags respectively. So but the idea is pretty clear. So whenever the timer operation is going on, and when the timer finishes its count and goes back to 00, so this interrupt is generated. Timer overflow for timer 0 and timer overflow timer 1. So this has the lower priority than timer overflow 0. And finally we have the interrupts for serial communication. So you'll find these interrupts being featured in SCON register. So in SCON register you'll see receive interrupt flag and transmit interrupt flag at position 0 and 1 respectively. So you could refer to SCON register or my previous videos where I've discussed serial communication. So timer interrupts have higher priority than the serial interrupts, and both these interrupts, because they are not generated simultaneously, so they have been placed at position number 5, so they feature in SCON special function register. So they will be generated there, so you'll get a signal of them becoming 1 or 0 in SCON register. Now incidentally, all these interrupts are a vectored interrupt, so that term is again very important, because if we study interrupts, we ought to know what interrupts are vectored, what interrupts are maskable. So vectored interrupt means whenever these interrupts occur, they take the microcontroller to a certain location where a subroutine or something of that sort must be written. So so microcontroller will go to that place to execute something. So when IE0 is encountered, it takes the microcontroller to 0003H. When TF0 is encountered, it takes the microcontroller to 000BH. For IE1, it takes the microcontroller to 0013H. So you'll see that technically there is a difference of 8 bytes between the vector addresses of one interrupt to the other interrupt. TF1 will take you to 001B. Again, very, very important from the point of view of multiple choice questions featuring in GATE and other competitive examination. And finally, serial interrupt will take the microcontroller to 0023H. So this needs to be committed to memory. So that was the priority of the interrupts there. Where do they feature and what are their vector addresses? Now, in order to control these interrupts, there are two special function registers in microcontroller. The first one being the interrupt enable register. So please understand this, as the name suggests, interrupt enable register is going to enable or disable a specific interrupt. If we wish to manually turn an interrupt on or off, we can do it from here. And the first thing first, the address of this special function register is A8. As I mentioned in the previous video, all the registers ending with 8 or 0 are known as bit addressable register. So this register is again a bit addressable register. I'll talk about the functions of each bit in detail. So you need to commit this address to memory, that A8 is the register address of interrupt enable register. So the 7th bit here is the main switch enable interrupt bit. Now if you make it 0, all the interrupts are disabled, and if you make it 1, then you have an individual control of all the interrupts. So this is going to disable all the interrupts completely and make it 1. So you make this bit as 1, and then you can individually control these other interrupts. So these 5 interrupts are what we intend to control here. So if we wish to turn the external interrupt 0 off, so we'll make this bit as 0, because EX0 corresponds to external interrupt 1. External interrupt 0. So making this bit as 0 is going to turn this off. So now this interrupt is turned off. So the highest priority interrupt becomes TF0. So And if we turn TF0 off, make this as 0, then again this will be turned off and the highest priority interrupts becomes the external interrupt 1. So again turning it 0 is again going to turn this thing off. So only 2 interrupts are serviceable now. So timer flag 1 interrupt is serviceable and serial interrupts are serviceable. So if I make it 0, again this is turned off, so we're left with only serial interrupts. So if we wish to do serial communication only and we do not wish to be interrupted by any other thing, so we'll make all these things as zeros and we'll keep this as 1. And how do we make these as 0 and this as 1? As I mentioned earlier, this register is a bit addressable register, so the command set B and then the addresses of the bits. So the address of this bit is A8, then A9, AA. So if I do set B A8 H, so this is going to make this as 1. However, if we wish to clear A8, we'll use this command. Alright, so we intend to keep only this bit as 1 because this, in this hypothetical situation, I only want the serial communication to work and all the other interrupts to be disabled. So that is how you do it. So key points are this register will help you turn off or on a specific interrupt, and again ET2 is reserved for future use. It is not being used in 8051. So these 5 interrupts are what we focus upon. So any of these interrupts can be disabled or enabled through interrupt enable register. So that was pretty easy. So the next register that I wish to talk about is the interrupt priority register. As I mentioned, the priorities of these interrupts are fixed like this in this order, but if we wish to change the priority of the interrupts manually, we can do it with another special function register known as interrupt priority register, whose own address is B8. Again, by looking at the address, you'll see that this again is a bit addressable register. So again, the priority of external interrupt 0, and this is the priority of timer overflow flag 0, priority of external interrupt 1, priority of timer overflow flag 1, and priority of serial interrupt is set or cleared by the user here. So because this is a bit addressable register, so if I clear, let us say B8H, which is by the way this bit, so the external interrupt 0 will no longer have the highest priority. It will fall at the lowest hierarchy, but the condition is that rest of them should be 1. So if all these have all these are 1s, so we are not wanting the priority of any of these interrupts to go down, but we want the priority of only the external interrupt 0 to go down. So we make it as 0 by running the command CLR B8H, and so this goes at the lowest position, and all things being equal, all of them are 1, so they'll follow the default priority. So that is how there could be one case where we want the priority of the overflow flag 0 to be highest, and then the serial interrupt, then we could make this bit as 0, keep it as 1, this bit as 0, and this is also 0 and keep this as 1. So making 0 here and 1 here, so only these two interrupts are left at the top of the priority table, rest of them will slide at the bottom. So that is how you can change the priority or fiddle around with the priority. And the bit addresses of these registers, by the way, can also be written as IP.0, IP.1. so if you run CLR IP.0, CLR or set B IP.1, it is equivalent to using their hexadecimal addresses. So having said that, these two special function registers IE and IP are going to control 8051's interrupts, and these interrupts themselves are featured at different places. Some of them are in timer operations, some of them are in serial operations, some of them are hardware interrupts featured as pins, and there's one last interrupt that I want to discuss, which is the reset pin. So reset is pin number 9 in the dual inline package of 8051. This has the highest priority. It is a non-maskable interrupt. Non-maskable means you cannot turn this thing off at any point in time. So if you look at the pin diagram of 8051, you'll find that reset is a pin, and if you give a reset signal to the IC, it is going to reset all the memory space to 00H. All the registers become 00H. Some exceptions are there that I want to mention here. The PC register will become 0000, DPTR will become all 0. Only the SP register will have a reset value of 07H. Again, very important. All the ports from P0 to P3, they'll have a reset value of FFH, and that's about it. All the other SFRs will become 00H. So exception of SP as 07H and exception of ports as FFH is the only thing that we need to remember. And the rationale behind is that whenever the microcontroller is booted up, the stack pointer always points at 07H, because that's the start of the stack, and all the ports are input ports, and input ports are made by keeping all the port pins as 1. So FF corresponds to that. So that was all I needed to talk about in interrupts of 8051. I hope this tutorial was of help. If you liked the video, give it a thumbs up. Consider subscribing to the channel. I'll come up with more such videos in the future. Till then, take care. Have a great life ahead. Bye.